Okay, now let's talk about vacancies. So interestingly enough, there's always a certain number of vacancies inside of your metal. It could be very, very small, but as we increase the temperature, more and more vacancies are going to form. That's because the atoms are going to start moving apart. They have more mobility. They're going to leave their crystal lattice positions. And when they do that, they're going to sometimes leave a gap. They're going to fill it. Now, each lattice site is a potential vacancy. Each lattice site is a potential vacancy. And so what we're trying to figure out here, usually, is the fraction of our lattice sites that are vacant at any particular time. This is an equilibrium thing, so it is like more of an average than anything else. It's not like it's going to be the exact number. It's just going to be very, very close to it. Now this fraction is equal to exponential, that's a function you can plug in your calculator, in parentheses, of the activation energy, which will either be in joules or electrovolts, over Boltzmann's constant, which is given here, and the temperature. Boltzmann's constant and the temperature. And that temperature is always, always, always going to be absolute scale. So Kelvin, if I give it to you in Celsius, you're going to have to convert. Okay, now before we jump any further, I want to talk about why you might want these vacancies. Think about steel, or we'll go with cast iron. Cast iron is, iron, but somewhere in there, it has carbon atoms. So that smaller atom right there, I'm going to put a little X in it. That's a carbon atom. And it has about 5 to 6% weight. Actually, depending on the cast iron type you have, it can be more or less. Now, how do those carbon atoms actually get into my iron? Well, what do you think? How did they get in there? They got in there through vacancies and how those vacancies move. So what happened is you heat up your iron, vacancies form, and then when those vacancies have formed, you put it into an environment, usually the heating process itself, that has a whole lot of carbon around it. And then carbon atoms are able to fit themselves into those vacancies. So carbon atoms finally fit themselves into those vacancies. So we want vacancies at times because we want to create these alloys, or we want to have a carbonized exterior, or we want to plate it with chromium. There's lots of different reasons we might want that. It's a part of the processing of a material. We're going to spend a whole lot of time on that later, but today we're just talking about how we get these gaps in the first place. And one key way to do that is through changing temperature. Now, this is one thing that has to be given to you. However, it can be determined experimentally. We're not going to do that in this class, but it can be determined experimentally. So one thing you might do is you might plot the number of vacancies, the fraction of vacancies, versus temperature. And you're like, well, what in the world? How did I get that? There's lots of different ways. X-rays, microscopes, the changes in density, changes in volume. There's various ways you could tell how many vacancies have formed. So don't worry about that too much for now. What we're going to see is that this has an exponential dependence. As we increase the temperature, the number of vacancies increases exponentially. And then if we do something which is called a log plot, where we log our vacancy fraction, and we plot it versus inverse temperature, because this is 1 over T, not just T, we can then figure out what the activation energy for vacancies is right here, because that will be the slope. Now, just to show you that, let's look at it beforehand. Okay, this is what my equation was. I'm going to step back a little bit. Here we go. I'm going to take a log of both sides, or the natural log of both sides. So I get ln NV over N is equal to ln of exponential of negative QV over KT. And maybe you don't know this, maybe you do, but natural log of an exponential of, let's just say x, is equal to x. Just get rid of it. So I get natural log NV over N is equal to negative QV over KT. Now this is actually, here, I'm going to make a new variable just to really drive it home. I'm going to call beta, and that's going to be equal to 1 over T. And so this turns into this equation, which was just a little bit of rewriting. You can see that this right here is just like y, and this right here is just like my x variable, and so this is my slope. It would be my slope. So hopefully you see where it's coming from. This is why we get a linear function when we do a log plot and we plot it versus inverse temperature. Now, you don't necessarily need to know the reasons behind it, but I want to explain that to you so you can see where it comes from. Okay, so I'm going to erase that. If you need to see it, luckily this is a video. You can go back in time. Rewind. Okay, and there we are. Now let's actually try this out. Now I've got all the numbers already here so you can see them, but if you want to, cover over this, don't look at it right now, and see if you can figure it out on your own. The equation's not too terrible. So what we want to know is we want to find the equilibrium number of vacancies in 1 meter cubed of copper at 1,000 degrees Celsius. 1,000 degrees Celsius. First off, that's the wrong kind of temperature. It's not the right kind of temperature. Okay, now things we're given are the density of copper is 8.4 grams per centimeter cubed. The atomic weight of copper is going to be 63.5 grams per mole. We know what Avogadro's number is, and they even are nice enough to give us the activation energy for vacancies, which we would desperately need. Now we've already done the first step pretty often. We have to figure out how many atoms are in 1 meter cubed of copper, because each of those atoms is a lattice site, and each of those atoms can move or turn into a vacancy. So I'll go ahead and help you out with that. We want to solve for the number of atoms, and that's simply going to be Avogadro's number times the density divided by the atomic weight. What that does is it takes Avogadro's number, which is atoms per mole, times the density, which is grams per centimeter cubed. Let's just look at the units here. That'll make more sense. We have atoms per mole times grams per centimeter cubed, all divided by grams per mole. Moles cancels, grams cancels, and I get atoms per centimeter cubed. And then when I convert, I get that I have 8 times 10 to the 28th sites per meter cubed. Now on the next slide, I'm going to go into how you would actually use this now to calculate the fraction of vacancies, or the number of vacancies at this particular temperature. But I want you to try it on your own. So pause, see if you can do it, like go back to the previous slide and see if you can plug in all the numbers for it. Remember, we have electrovolts here, so make sure you're using Boltzmann's constant that has electrovolts in it. Okay, so 3, 2, 1, and you're back. Hopefully it went well or terribly. You know what? You can choose what you want it to be. And we'll see if we can do this now. So before we had number of vacancies over my number of lattice sites, but since I want to solve for number of vacancies, I multiplied both sides by n. And I already have all of these numbers. As long as I'm very, very careful to make sure I convert from 1,000 degrees Celsius to 1273 Kelvin. Celsius is equal to Kelvin minus 273, or vice versa. And then what I get is that my number of vacancies is going to be 2.7 times 10 to the negative 4th times n. If I plug it in there, I'll have 2.2 times 10 to the 25th vacancies per meter cubed, which sounds like an awful lot. And it is an awful lot. It's a humongous number of vacancies. But it's still a very small fraction of the total number of sites. So, I hope this helps you. Thank you for listening, and I'll see you all next time. Bye-bye.